3, 2, 1. Isn't it wonderful when you can watch a beautiful video and see it made at the same time? Oh man.
Saw online, note the big huge foam hammer and this thing, and watch what happens when I power it up. Up pops a mouse's head, whack it down and score points. It's literally one of those whack-a-mole modules. Now if I power this up my power supply is bottoming out at 3 amps, 22 volts, and that is quite a beefy solenoid coil, but it's still enough. It pushes it up, you can still push it down, you can whack it with the hammer to actually let the machine register it's been hit, but you wouldn't want to leave that powered too long, particularly given that it is heavy windings. Well, I'll cut this off and we can take a look at the windings, if it stays powered too long, it's going to get very hot. I put a wee pad here, by the way, a little foam pad, just to make this quieter. So this is not Mickey Mouse. It just looks a bit like Mickey Mouse, has the same haircut, but it's definitely not Mickey Mouse. So let's take a look at the construction of this. Now, the wiring loom going up to it has 2 heavy wires. There for the 24 volt supply that kicks it up. It's switched by a MOSFET. I'll show you the circuit board in a moment. And then it's got a little 3-wire loom which has current limited 5 volts for the infrared LED. Let me zoom down on this. Can I zoom down this? Give you a closer look. We have the infrared emitter and we have an infrared receiver. That's all that's on this circuit board, just an emitter and a receiver, and there's the bottom of the solenoid plunger so that when it pops up, the beam is made, and then when you whack it with the hammer, or if it turns the solenoid off itself, if you don't get there fast enough, the beam is made again. Okay, let's go back down to a more sensible height. Oh no, let's not go there. Has that focused? Just double checking. Yeah, there we go. So we'll look at the construction. It's interesting to note there's a little screw in here that's holding this in, and there's a position. There's another hole on the other side, but there's also an indent in the correct position for putting another screw in. I get the feeling that this screw is going to chaff that plastic over time. Personally, I'd put a little bit of sleeving over it, just heat shrink sleeving or something if there's room in there, just so it gave it something to rub against. Maybe that'd be a bad thing though. Okay, let's. That is a Phillips screw. Let's grab Phillips. Let's cause an avalanche and drop a screwdriver on the floor. And I shall take this screw out. It appears to be just tapped in. Is it a self-tap, or have they drilled and tapped this? It's quite long. This is good in a way. It appears to be drilled and hopefully tapped. Here we go. There is a ring of foam on the bottom to absorb the impact when small children smash it with force, or actually when their dads smash it with force. There is a, what looks like a split ring. Well, that's not the correct term, is it? Oh no, actually it's a grub screw. It's a grub screw going in through here to actually lock it into the plastic. And this is basically, this metal tube is the solenoid core that is going to go up there. Yeah, there's the other hole, the indent for drilling that they've not actually done that with. I guess this might actually be self-thread cutting. Let's take a look at the solenoid, then I'll show you the circuitry. I'll show you the circuit board for controlling it. I bought the whole thing, but only one of these pop-up things because I have no need, you'd need 8 for the game, and it would add up quite quickly because you're approaching the cost of the game plus the cabinet. So let's get this off. And here we have, it's got a thermal fuse. That's good. I didn't know it had a thermal fuse. I'm very glad it's got a thermal fuse if it gets too hot, because that's what could happen. I was wondering what protection there was. What's it designed to trigger at? Where's my magnifying glass? 85 degrees Celsius. Don't know if you can see that. Don't know if you're even interested in seeing it. So that is the solenoid. It's just basically coarse wound wire. And a thermal fuse in line. Glad about the thermal fuse. Very glad.
Stick with Cardre.
Envisaging these games just bursting into flames if the processor crashes. Worst case scenario is the processor crashes and powers several of the things simultaneously, and they just jam up, and then it would knock those thermal fuses out. I would have considered something like a PTC thermistor on the circuit board. But then again, you'd have to balance it so that it would allow normal operation, but if it stayed too long, it would trip. But that thermal fuse is good. It's I don't think it's self-resetting. I think it's just a one-shot thermal fuse. Anyway, let's take a look at the circuit board. Now you've seen the construction of the whack-a-mole unit. Can't really call it whack-a-mole because that is an official name, like Sweet Licks by Namco. Everybody copied the same style, but themed it differently. So here is the scoreboard. Nice big digital readout. And here is the control PCB. And this is based on, presumably as a microcontroller under this warranty label. Oh, it says 2025. Okay, 4th month of 2025. So, taking a look at this, the display is serially driven. It's got a dedicated serial driver chip with one resistor that sets the current for all the LEDs, and it seems to take data in, and presumably it loops across and then sends the data through to the next display, because these two can be parted if needs be. Probably standard modules for many arcade games. Let's zoom down on this. No need for a close-up photo because it's so big I couldn't really even take a close-up photo of this. It's just too big to take a close-up photo of, so I shall just do it live. So what we have here is we've got the power connector, which is 5 volts ground, 12 volts ground, and 24 volts ground. We've got another 12 volt ground connection going out here, not sure what for. We've got 12 volt ground, 5 volts, and transmit and receive for serial communication with something, I don't know what. We've got some buttons down here. We've got enter, next, up and down and up, for changing the settings. But this thing, for a start, see the anti-static symbol? It came in ordinary bubble wrap. It didn't come in anti-static packaging, which is really annoying because this was about £40, this circuit board, at least. But it didn't come with any data about the circuit board at all. That's not terribly helpful. However, we can work things out. I'm worried about this thing that says key. Is it got a facility for a keyboard? Don't know. But key, hopefully not a security key for proprietary game control. I don't think so, though. But we've got a sound output here, and we've got an amplifier chip here, and possibly this is a dedicated power supply section for generating the supply for that with a little volume control. We've got a programming port, ISP, and then it looks like we've got a memory chip here. It's a Winbond. What's that down there? Is that that's an STC?
I'm in the whispering
8G1K D8. This might be a microcontroller dedicated towards sounds. I'm not really sure. I mean, technically speaking, with a bit of skill, you could actually fit the whole lot in there. But I guess there's a microcontroller under here. There's no warranty in this. Let's get the tweezers and try and remove this label from here. Is it just going to rip? Yes. It's ripping. They're not going to give them the money back now. That's fine. I'm not even going to try and get the money back. It's not. It's disintegrating into pulp. That's not going to happen. Just give me a moment. I'm just going to pause and take that off. 1 moment, please. And resume. So the chip is an STC 8G2K64S4, which is a very common 8051 core microcontroller. That kind of also tallies up with them using that STC chip over there. It means that it just fits into their programming skills. Usually when you design something, you want to stick to one standard microcontroller range. It just makes things easier. I've got that label stuck all over my fingers. It was very, very tricky to remove. And then, because that was lightly etched, I had to rub it with heatsink compound and then wipe it off with a cotton bud to be able to read it in the first place. But that's got Watchdog, it's got all the power management, it's got everything. Onboard debugging, it's actually a very capable little processor. Quite neat. Anyway, now where am I? I've got other connectors. There's 3 MOSFET positions here. This one appears to be going over to here, which is marked prize, so it's possibly for controlling a prize dropping mechanism. And then there's a couple more MOSFETs for auxiliary outputs. We've got the coin mechanism, which has got 12 volts ground and the signal back. We've got the display driver, and we've got a ticket driver, which is 24 volts ground, and I'm not sure if it's just the data it's sending out, or it's actually just if it's actually controlling the motor and the optical feedback. I would suspect that it is direct control of it. Then we get the MOSFETs and all these inputs, the ones that are going to this little circuit board on the bottom of the unit. And since I'm not going to reverse engineer the whole circuit board, I may look at this later on though, but I've reverse engineered just one of these channels just so you can see how it works, how the sensing works. And there's a whole row of LEDs missing from here that I thought would be quite nice. It's a shame they've actually removed them, but then there's a lot of components missing from here that are for all the different features that might be added with these connectors. Receive, transmit. I don't know what connector 10's for. Don't know what any of these connectors are for. None of them are. They're just reserved for purposes. It's possible this PCB is used to control other games as well. But anyway, let's take a look at the schematic, or at least a bit of the schematic, the bit we're interested in. With MOSFETs and opto isolators. Well, it does have opto isolators, but it's also got the optical detectors. Here is the bit of the circuitry we're interested in. I'll make it nice and square this time and kind of line it up in the middle. We've got 3 voltages in play here. 5 volts, 12 volts, 24 volts, and 5 volts again. So for the little circuit board on the bottom, we've got 5 volts is driving the infrared emitter continually via a 330 ohm resistor, and that then shines on a phototransistor. Or actually, no, that's wrong. I'm talking about this bit over here. Right, let's go back. Right, so let's start with the circuit board at the bottom. Right, okay. Ignore that bit. I was wrong. That is controlling opto isolator, but this is the bit we're interested in. So that's the little circuit board at the bottom that detects the solenoid go up and down and whether you've hit it or not. So we get the 5 volt supply, 330 ohm, going to the infrared emitter, and then the detector photodiode here. There's no fancy modulation by the look of it. It's simply pulled up to the positive rail 10k, and when it's bright enough, it can pull this low enough that the transistor is turned off. And there's a capacitor here just to provide a bit of filtering. There's the missing LEDs and resistors that would have been so useful. Let's just guess the value would have probably been 1k based on other stuff on the circuit board. So normally, with the plunger down, this beam is broken. This is a high resistance, and the transistor turns on and it pulls this down so it's low, and the microcontroller sees that's low. That would also light the LED to show the plunger was down. When the machine fires the plunger up, this beam is allowed to make, and that then pulls the transistor low, turns it off, and then that would let the microcontroller sort of pull that up high, and it would see that the thing had gone up. And if before it's turned that solenoid off, if it sees that the plunger's gone back down again, it knows it's been hit, and it will actually register that you managed to hit the thing in time. The coil itself, here's the coil. It's so big and beefy it just feels inadequate just to draw it as that. But that's okay. But it's a monster of a coil. It's huge. But here is how it's driven. The microcontroller pulls this pin low, and there's a 330 ohm resistor and the input to the opto isolator. Let me show you the opto isolator on the circuit board. There's a row of the opto isolators. They're also used for these MOSFETs as well. Note that each of those is a anti-back EMF spike. It's not so much EMF as a collapsing field spike suppression diode, and this actually has 2 diodes underneath, which is quite interesting because it's a nasty, very nasty inductive load for switching electronically. So when the microcontroller wants to pop the figure up, Mickey Mouse, it pulls this low, that activates this opto isolator. The opto isolator then provides current via 1k resistor from the 12 volt rail, which means it can use standard IRF 540 MOSFETs, just generic cheap ones, not the sensitive low gate voltage ones. And that's normally pulled down with a 10k resistor, but when the opto isolator is on, it pulls it up via that 1k resistor and turns this MOSFET on. The MOSFET energizes the coil, and it's notable that there is that freewheel diode there for the collapsing field, but there's also protection across the MOSFET as well, which is quite interesting. It has an internal diode, but they've added an external one just for double belt and braces protection against those nasty inductive spikes. The reason for that is when you energize a coil like this, it has the core in it and it creates that strong magnetic field. When you de-energize it, the polarity reverses as it collapses, and if there's nothing to clamp that, if there's no shunt across it, it could produce a very high voltage spike here, and that could potentially damage the MOSFET. But there we have it, there's not much else to say, that's really it. All the rest of the magic is done in software, and that is locked in here. I kind of want to know what the sounds it makes are, but the only way to do that is to power it up, and unfortunately, I just know that the first thing it's going to do when it's powered up is it's going to look to see if all the solenoid plugs are down. It might even do a self-test. It might, I mean, that's what I'd do if I wrote the software. But having said that, some of these games, including many of the American-made games, arcade games, they're terrible. They're self-diagnostics. They don't detect faults. They just mince away as if nothing's wrong, despite the fact people can't play the game because it's defective. It's very odd. Major league, including ones that let you effectively cheat the game. The software in these is usually terrible, but maybe this one is better. But personally, there's 8 outputs. I would basically just start the game by just pulse. I'd pulse it, see if the beam broke. As soon as I saw the beam being made, should I say, I would then step on to the next one. So you'd see a ripple, it would go along the solenoids as it just self-checked. But that, I would guess that hopefully if it detects a fault, it might play around that one that's not working by just basically popping the others up and just removing that one from the game. Or it might just play and pretend it's there and just register as a win because it didn't see it go up. Who knows? But there we have it. It's interesting. I'll provide a link to these just for your novelty. I don't see you rushing to buy one anytime soon. But it's just a kind of silly fun thing. They also do illuminated bezels you can put these into as well. But that is it. What do they call these? Is it animal guard or something? They had a strange, or fraud guard they had for these. Strange name. But there we have it. Interesting stuff. You know, it was good to see. It was interesting to look at and see their construction, particularly when you've seen them in the arcades. Lots of fun just to see it in the flesh, so to speak.
Next question.